all this details, we're starting getting ahead of ourselves. Let's see if I can get us to the place where we can start talking about results in just a moment, though. One thing I wanted to talk about was, though, something we're going to set up when we go a step further, but this is whether or not our covariance matrix is saturated. So we have a model there. We know that the exogenous variables part of it is saturated for those variables, but what about the other ones? So the way to think about that is to take all the variables that are in the likelihood, and I said Levon puts everything in the likelihood, so just count up all the variables, endogenous plus exogenous. Right? So we have 4. That covariance matrix is size 4 by 4. Right? So the alternative model, or the saturated model covariance matrix, would have how many terms in it? 4 variances, 6 covariances. Right? So there'd be 10. And the saturated model mean vector would have 4 means to it. Right? So what you did in homework for model 3 would have the same 14 parameters. And this model can have 14 parameters is what that is. So what we're going to find is that one way to ensure that our model is identified, so this is a necessary but not sufficient condition for identification. Our model parameters take these means and variances and covariances and turn them into things that we like to interpret. They turn them into slopes, it turns them into intercepts, it turns them into residual variances and covariances. Right? So we can't have any more parameters in our model than we have parameters in our saturated model. So our specific model itself can't have any more. We can be equal to, and if we're equal to, sure enough, we'll fit as well as the saturated model. But that's kind of the trick with the multivariate model. Our model itself needs to have that equal to or less than the number of parameters they would have in our saturated model. So here we have 4 intercepts, 1 for each variable. Now the endogenous values, we really call those intercepts. The exogenous things, those are more means, but an intercept in an empty model is a mean. We learned that already, right? So empty model, intercept equal to means. We can kind of interplay. Intercept in a non-empty model is a mean when all the x's equal 0. Right? So that's the difference between intercept and mean. But we have 4 intercepts. We have 4 regression slopes, right? HSL and CC on performance, HSL and CC on usefulness. That's 8 model parameters. We have 2 residual variances, 1 for each of the dependent variables. We have 1 residual covariance between those dependent or endogenous variables. We had 2 exogenous variances between the exogenous variables, or with 1 for each of the exogenous variables, and then 1 covariance between them. So if you add all those up, guess what? We get 14 parameters. So believe it or not, what we've just done is estimate a model that fits as well as the saturated model. So we don't have model fit. Better yet, we have model fit. It's perfect. Our model fit is perfect. We may have no good results to talk about. We may find that everything equals 0 in terms of slopes that we're interested in, but we have perfect model fit. So we don't have to talk about that. Right? So the process, if we think about the process we're in, we're making the hypothesis, we're formulating the model, we estimate the model, we look at model fit. We're in the model fit stage, check. Model fit is attained, it's perfect. We have just created a perfect, hey, look at that. If this is your first multivariate regression, you did it perfectly. You got fit perfect. You can't get better than that, right? Anyway, so don't even need that. So we'll move on to the parameter estimates. Now these parameter estimates are what we call unstandardized estimates. Or in regression, we just call them beta weights. Right? It's funny how now all of a sudden we have all different labels for all the stuff we knew and loved before. Unstandardized just means what we get out of the raw data. Right? So everything is on the scale of the units of the variables involved. For instance, this right here represents the slope for high school math experience predicting mathematics performance. Does anyone want to interpret this value for me? It's like you would interpret it in regression. Lou, do you want to? No, sorry, I see you're thinking about it. You can think of it.
Yeah. One unit is high school math experience in place techniques. 1 point
Exactly. For every 1 unit of high school math experience that goes up, mathematics performance goes up by 0.984 units. Now, what are the units again? This is one course. One course of high school math leads to almost 1 point more on a 20-point test. So if you want to ace the test, you should have taken 20 high school math courses. Yeah, no, that's not quite right. So let's think about, that's exactly right. Thank you, Lou. Who wants to do this for college math experience? On the prediction of college math experience, prediction of mathematics performance by college math experience. Anybody? I think I just heard performance. Maybe they do. Does anyone know who this is? This might be Barbara Kurt. No, I don't know. Who's teaching this? I'm trying to think of, I know the voice. I should just go over there and be like, I'm sorry, I'm loud. Anybody want to take a shot? Megan, help me out here. Oh, she's got a mouthful. I'm gonna call on people. Hong Ling? Oh, yeah.
For every 1 unit increase in college math experience, you would expect to see math performance go up by 0.079.
That's right. So 1 unit more of college math brings you 0.079. Does that mean, like, if we look at 0.079 versus 0.984, that college math matters less? No. Because what's 1 unit of college math experience?
Credit hour.
1 credit hour, right? And how many credit hours per course? We don't really know, but I'd go with maybe 5, something like that, right? At least. Right? So 5 credit hours of college math. It's really, if you want to talk about how much more 1 course is, it's not 0.079, it's 5 times that number. Right? And that's the thing about unstandardized or raw direct effects. They are in the units. They're a unit full, right? They matter. The units matter. We're going to see the opposite of that in just a second, but let's just take a look at everything else. What does this mean? So we've got each of these is the standard error. We could form a Wald test with each of those. We're using robust maximum likelihood. All this that we've learned before still applies. We can figure out which ones are significantly different from 0. It appears off the top of my head that all 4 regression slopes are significantly different from 0. So not only does our model fit, but we may even have a story to talk about here. The story would be high school and college math experience predict college use, perceptions of mathematics and mathematics performance. Yeah, that's your story, essentially. All the other terms are descriptive, right? We have our residual variance out here for each of these. We could describe Rsquared, right? Had we fit the empty model and then compared, we could come up with that. Actually, there is a command in Lavon that I didn't show you before that will do the same and tell you the R-squared for each of your dependent variables. All right, what proportion of variance in that variable is accounted for by the prediction that you're doing. What we get is an R-squared for each residual variance by itself. What we do not get is an R-squared for residual covariance. That's a little weird. When you get to multivariate, or those of you in multivariate, we actually can come up with one of those too, but something called a generalized variance. We won't talk about it here. And same thing over on the left side, the exogenous variables. This is the variance of high school math experience. This is the variance of college math experience. And you can see, because the relative variances are so much different, those units really do differ a lot, right? 1 more unit of high school math experience is a lot. 1 more unit of college math experience, it's not as much, right? The variances are different. So if you're getting it from this here, what's the unit mean? It's something related to variance. Actually, it's standard deviation. If we took the square root of each of these numbers, we'd know the units of that variable, what a unit meant. We also don't see on the path diagram our intercepts or our means from before. Questions on the path diagram? Cool. So now, here's the thing about units. We just described and interpreted that the effects of high school experience on performance. What's it? Yeah, performance. But take a look at what happens more specifically, right? You see, we saw that effect that Lou interpreted was 0.984, right? For every 1 course more mathematics in high school, your score went up 9.98, almost a full point. But for every college unit that you took, every credit hour you took, it went up 0.079. Not course, but credit hour. Right? And take a look. The standard deviation of each of these is very different. So what we'd like to do if we wanted to compare and contrast them is we'd need to put them onto a similar metric or similar units. And that's where standardized comes in. The standardized says essentially, instead of saying in terms of units of y per units of x, it says standard deviations of y per standard deviation of x. Right? Now your standard deviation may be different, right? The standard deviation of high school experience is 1.31. The standard deviation of college experience is 0.58 or 5.88. But for every one of those standard deviations, we're talking about how much y goes up in terms of its standard deviations. Right? It's a useful metric for us. It's kind of like a z-score, and that's exactly what we think about here. So in Lavon, you can get, in the summary statement, you can put an option in that says standardized equals true. Right? So remember in the summary, this is how to get all the output. Right? It starts with fit measures, tells you all the model fit stuff at the top. This standardized equals true. In the parameter estimates window, it gives you the standardized effects at the right-hand column of your output. So while you're looking at a regression slope, you can see the raw value of it, but then you can go all the way to the outside and see the standardized value for it too. And more often than not, I tend to prefer reporting the standardized effects when we report these things. But ultimately, it's all kind of context specific. You may want to report the unstandardized because that's what's done in your field, or perhaps that's what the reviewer asked for, or who knows what. So you're welcome to report it. Just remember, it's all the units that matter, right? How to interpret it depends on the units. Just like that exercise we just engaged in where Lou described units of high school and Matt described units of college, essentially, described the two. There is another function you could just come out with. You could use the function that's called standardized solution. This is a little bit more in depth. It will give you a listing of all the parameters, even the ones that are fixed to 0. And it'll give you the standardized estimates, and you can actually ask for different versions of that. And sure enough, just to make things more ridiculous, there are different versions, right? Standardized.all is pretty much what we think of. It standardizes by making it the description units of y and standard deviations of y per standard deviations of x. std.nox means standardize y, but don't standardize x. Right? So your description of the beta weight would be something along the lines of, as x goes up 1 unit, y goes up this many standard deviations. We use that when we have x's that don't have units, like gender. Right? 1 more unit of gender really means men. Right? Right? So the interpretation would be that men have a difference in performance of x, y, whatever standard deviations y would be, over women. That's essentially it. So that's about the only time we do that. This standard.lv, it works the same as standardized.all, but it's used for latent variables. And the reason for that is that in the latent variable world, we have to define what the variance of the latent variable means. Whoa, yeah, that's a little weird. When we get to next week or the week after, depending on how long it takes me to get through these slides, measurement models, we're measuring things that don't directly exist, so we sort of have to kind of define the metric that they're on. What's their variance? So that's why that one gets a little weird. Right? It takes the latent variable variance, but it may be standardized in one way or it may be standardized in another way. So it gets kind of funky. Questions on standardization? Okay. Here are the interpretations for each of these effects. Each of the effects that we interpret, these are in the big text, it's the unstandardized. In the little bullet on the other side, it's the standardized. Some coefficients just don't make sense to put in standardized form. Looks a little weird. But one thing I'll note is all the interpretations that you see here are consistent with what you used in linear regression. or an analysis of variance. All the things, in fact, the first homework this year, all of those interpretations followed from it, right? I made you say, what's the value, what's the intercept mean? I made you interpret that. That is what the intercept means here. It's the predicted value of your test score when high school and college math experience equals 0. So in better terms, a person who never took math in high school or college was expected to get, bless you, a little over 8 points out of 20 on this test. So evidently the test carried content that was before high school. Because somebody who never took high school or college math could get 8 points on it. Or better yet, guessing. I don't know. Anyway, same interpretation, same thing with each of the other effects itself. Here is just kind of a difference. If we interpreted the standardized coefficient for performance, the unstandardized, the standardized is 0.438, which really means for every 1 standard deviation extra of high school experience, then test scores went up by 0.438 standard deviations. Right. What's the standard deviation? Well, you got to go look that up. Right. But that's where the standardized coefficient matters. And the same thing with college standard. Any questions? So all this works the same. Here's our R squared. There's a way that you can get R squared. This is back, I put these slides together actually before the semester started, believe it or not. I was like, well, there's a baby coming in my life and I need to get on top of things. And so I prepped like 8 or 9 courses. And then I haven't prepped again. I'm going to start prepping again tomorrow morning, though. But that means I didn't fully know Lavon like I do now. But if you take your model output and put it in this inspect function with an option that says what equals, and in quotes, little r2, it'll give you an R squared for each of your dependent variables. Another way to do that is in that summary statement. In Lavon, when we looked at this part right here, this summary right up here that we saw in Lavon, you can put another comma on there and put, I believe it's R squared. The word R squared. I can't draw that little. I can't write anyway. The letter R, the word squared, all in lower letters, equals, and then capitals TRUE. R squared equals true. And then it will spit the R squared out in the summary statement at the very end after you get past the parameters. So that was a question on homework 1 also. What was the R squared? And I purposefully hid those values from you because any option that you chose to figure those out would lead to a good result. Number 1, if you knew enough about Lavon or inquired about it, you'd find it out on your own and you'd learn about Lavon that way. Or number 2, if you realize, oh, I could just take this R squared formula at its root, if I figured out what the original variance would happen to be and then subtract it from it, the residual variance after I did the regression, and divide that by what the original variance was, I can compute the R squared myself. So it's why I did not tell you those in the first place. R squared is very much tieable to our data. It just seems to float away from it as we go on in life. I think we lose the forest from the trees when we teach these things. I know I do. So I'm trying to keep pulling it back into data, what we're trying to do. Okay, so how's it going? Questions? R squared for performance was 0.24. R squared for usefulness was 0.024. One was 10 times the value of the other. And that's common. How many of you have reported R squares for your research before? Anybody? Yeah, what's your values like? In your field, I should say.
Higher than that.
Higher than that, that's good. Okay, 0.3, 0.4, something like that. That's good. Those are good. Yeah, these are fairly common for a lot of the path models you see. Minimal effects, usually, in social science research. But if you have better effects, that's awesome. And the best effects I find are always in the textbooks. So, right? So those seem to be, like, the first homework effect was 0.996, which I used to try to have this thing where I would create a wall in my office. I'd call it like the R Squared Hall of Fame. And if you had an R-squared that was awesome or like up above 0.9, I'd say, just bring it to me and I'll put it on my little wall of fame. And I stopped doing that because it was just empty. Right? It's just, there's no R-square that's reportable that's really that great. Is this going okay? Am I at a good pace here? Trying to make it somewhat interesting, trying to not bore you to death. Here comes the pretty boring topic. Identification of path models. Yeah, if I just underwhelm you, then I figure like, or better yet, if I set the bar really low, oh, this is going to be terrible. This topic's really esoteric. Then if it's at least marginally better, maybe you'll feel like, hey, that wasn't so bad. It's like the dentist. Oh, we're going to have to do the root canal. And then like, really, it was just a tooth cleaning or whatever. No, anyway. Model identification is a statistical topic that basically says the parameters that you see are unique. They're unique values. Isn't that weird? You can have results that aren't unique. The reality of it is unidentified model means you have far too many parameters than you have essentially things to find them. And what we had this is sort of tautological. What I'm going to describe here kind of relates back to why we were counting parameters before. But that's kind of the gist of it. If you have 14 numbers that you can get out of a model, like a saturated model has 14 things, there are only 14 things that you can come from it. It's a system of knowns and unknowns, right? You can have 14 model parameters, 14 saturated parameters, 14 model parameters that take those values and put them into interpretable things that we report. Right? So there are two types of identification. One is just that, the counting. Sometimes we put another, of course, nothing is as easy as like counting. We can't give PhDs for people who count, although that'd be awesome. All right, so we have to confuse it a little bit, and that's what's called the T rule, which means count it up. How many parameters does your model have? How many does the saturated model have? There you have it, right? And this is part of the reason why a lot of my questions are, how many variables are there? Or how many endogenous variables? Because that sort of says some things about the parameters. The other is a little bit more straightforward. That first one was global. T-rule counting is global. The other is local, which basically says, in a nutshell, you can't have paths that give you circles in the path analysis. And so let me see if I can describe that a little bit better. So the T-rule is counting. But nobody ever, my wife likes to call this stuff job security, right? If you can confuse it and make it confusing enough, then people will pay you to do it for them, right? Which is terrible. I think you should learn it, but, yeah. Basically, you need to know that the number of parameters in the saturated model is equal to or more than the number of parameters in your model, right? Your model has to be less than the saturated model parameters. There we go. So here, this is what we saw before. Our model happened to fit that. There are several different versions of the status of this. I think I talked about this a little bit last week. There's just identified, there's over identified, and then there's under identified. I don't know if I talked about it. I had it in the quiz last week, and I was trying to get you to think about, trying to find obviousness, and this is the one I didn't make as obvious as I should have. Just identified means you have an equal number of parameters in your model to the saturated model. Just is equaled, right? Over is where the number of model parameters in the saturated model is bigger than the number of model parameters in your model, right? That means you have more unknowns than you have equations. Do any of you get, sorry, I'm sorry to interrupt. Again, I'm on call. And this is an emergency text message. You ever get those? Like when you get them, do you get them like 4 times for the day? Like my phone delivered this at 11:50, and this is the 3rd time it's now thinking it's delivering it. No, my phone. Anyway, about time to invest in new technology, I think. Over-identified. So just identified is equal. Over-identified means you have more knowns than you have unknowns, right? And remember in elementary algebra, you would talk about a system of equations. You'd have a series of things you knew and then equations for them. That's essentially what we're getting at here, right? If you had more knowns than you had unknowns, you could solve that system of equations. Right? Linear algebra kind of did that thing on steroids, elimination and back substitution and so forth, but it's the same idea. So over-identified and just identified are awesome. I'll give them a red star here. That means you can run your model. Under-identified is the problem. You have too many parameters you're trying to estimate and not enough covariances or means to estimate them from. Right? That's too many unknowns to solve. So that's where we have problems. So count up the numbers, should work. Most of the models that you do will be fine, particularly with path models. Where we run into issues are structural models or structural equation models where we have latent variable things and not things, and it starts to become a mess. That is the global identification, right? The count. The local identification gets a lot more complicated. Right? Each part of the path model has to be identified. And by each part, really we're talking about each variable in relation to all the variables it's with. So for most research designs, I say that it's a terrible throwaway comment, but most of the ones that you see in the social sciences, counting is enough. That's fine. It should suffice. Because what we'll be running are models that are said to be recursive. Recursive path models are good. There's another bad term, but recursive. Really, a recursive path model is where the direct effects, if you were to take any variable and follow the direct effects, right? If you only think of the direct effects as one-way streets, you'll never make your way back to the variable itself. Right? Right? Which sounds odd because I want to call that recursive, kind of like there's a curve there or something else, but really that's if you get back to it. But really, recursive is where you can't get back to where you started. Right? Those are good. If you have a recursive path model and you have the T rule or the count satisfied, equal to or less than number of parameters than the saturated model, you're identified. You work. If you have a non-recursive path model, it may not work. In fact, most of the time it doesn't work. So here, this is a recursive path model right here. Right? If we were to start at high school math experience, we'd take a walk down where the one-way street is to college math experience. We'd get over to math self-efficacy, and we could not get back to high school math experience because they're all one-way streets. Right? Same thing with high school math experience, or same thing with college math experience here. Actually, we could go the other way. If we went high school math experience, went to math self-efficacy, we're done. Same with the college math experience. If we went right here, it couldn't work. Now, here's an interesting thought. What if I went and put a little arrow like this in my diagram right here? Oh, I want to estimate a residual covariance between these models. Take a look what happens. I take a walk down this path right here, and all of a sudden I can get on this little double arrow and get back to math experience. Can't happen. So what that local identification is telling you is you can only have one type of effect with another variable. Right? It can either be direct or it can be indirect, right? Direct, or it could be non-directional is what we really call those. Right? You have a beta weight or a covariance, but you cannot have both. Here's another example. And this may be something that you think about, because it happened for me. I came into college having absolutely zero math self-efficacy. And there are days that I'm doing my research, it's about zero as well. I like to have that humbling experience every day. That's a lot of fun. It's where growth happens, and I've got a lot of room to grow. But, so you got high school math experience here. You may get to college. High school, you had to follow the curriculum. Everybody essentially has a standardized path now. The curriculums are a lot more standard. Get to college, you could pick a major. Maybe you, like me, and all of a sudden you take a stats class. Whoa, I can do math, you think, right? So college math experience upped my math self-efficacy, which then caused me to take more college math because I could do it. Like, hey, I never knew I could do it before. I can do this, right? Which is completely plausible. But if you have data from a single time point, not longitudinal, right? This is a single time point. This is math experience, today, and self-efficacy today, there's no way this model can be identified because you can't simultaneously see an increase in both variables from it, right? And so actually, in my previous version of these slides, I did this model in M+. It estimated it, but it gave me a term like our beta for the beta weight. The standard error of the beta weight was something like 3 million, right? And remember, that's a variance. It's like if you take the standard deviation, the square root of that, it's like a standard deviation. It should be somewhere in the scale of these variables. None of these variables had scales in the tens of thousands. So really, there's something mathematically going wrong that the estimator was trying to get to work in the likelihood, and because of the way we decide for it to stop, it allowed it to go forward and give me a result. But we have to know better than that. That's why I'm telling you this. If you read the book, the chapters from the Kaplan book, again, those are the ones that are optional, particularly if you're a REM student and more interested in learning more in the behind the scenes for this. Not that you have to. Sorry, I'm singling out you REM students. But they give you the mathematics behind it. To figure this out, you have augmented matrices, and you have to find the row rank of these and so forth, and it's a mess. But generally speaking, and actually, if I can't do it off the top of my head, then it's something to like read it, and okay, I'll come back to that when I need it. But if you want more of the behind the scenes behind this, that book is very good for it. Ironically, it's like this thick, right? The Klein book is like this thick. The Kaplan book is that thick, but it does it all in matrices, and so that's why the shortening happens. Questions on recursive versus non-recursive models? Okay, to summarize, do this. Make sure your model is non-recursive. That just cuts it down. If you had a longitudinal data, you could have essentially, if this was time 2, time 1, and this is time 2, or actually better yet, this is also time 1. If we didn't have this path, but maybe we had, bless you, college math experience over here at time 2, right? You may have this feedback loop happening. You may observe it longitudinally, but from a single cross-sectional point of view, the variables aren't the same. You can't really do that. They are. It's just not identified. Okay, so this is also the part where, when you start thinking conceptually, it's the conceptual model versus the hypothesized statistical model. In concept, you can come up with a hypothesis that's non-recursive, where you have this loop. It's pretty easy to do, and usually it's your advisor. Actually, it's not an advisor. Remember that crazy committee member that's on your committee? You know that one I was talking about before? Right? It's that person. Right? That you go into your defense and they're like, I think you should be doing this. And then they talk like a Muppet. And then, right? That person usually tells you, and they draw it out on the board, and there's this big loop to it, right? And it may be, usually because they're crazy, they'll have like 15 variables, and the 15th one will loop back to the first one, right? So it takes a while to get the loop in there, but it does. Stay away from their advice, because that makes estimating these things impossible. You'll actually see, I'm going on a little bit of a tangent, but it's related. People have tried to develop estimators just to even estimate these things that shouldn't be estimatable. Right? Some things are partial least squares. I don't know if you've ever heard that term before, but some people will say that. PLS. People love it. I don't know, logically, it just doesn't seem to sit well with me. I can see it if you have it over time, but in a snapshot of the cross-section, it doesn't work. If you have a non-recursive model, if you have a recursive model, no feedback loops, you're awesome. If you're non-recursive, you're not. So in the case that you're awesome, you just need to make sure that your number of model parameters is less than or equal to the number of unique covariance elements. All right, shall we put it all together with the final model? We're going to put all this together and put it into the big path analysis itself. Here is my path model of path analysis. Path diagram of path analysis. We would call this a meta diagram, flow chart. So here's how it usually works. You formulate a hypothesized model, all right? And is the model identified? If the answer is no, you kick the computer just because it's there, and you go back and reformulate it, right? But if the answer is yes, you move to estimate the model. Right, so you build it all in Lavon, you get your data in there, which is no small feat, right? I mean, that still takes a lot of effort and trial and error. And then you'll find you have to ask, did the algorithm converge? I remember the convergence of maximum likelihood. We have to find the maximum. And so you'll find if the algorithm didn't converge, you usually have to say no. That's where you really start to kick the computer, right? You go back and you tend to, non-convergence can really mean a number of things, but it can actually indicate non-identified models. So when I tried to do the M+ thing this year with Levon, I gave it the non-identified, that recursive model with the feedback loop, and Levon just didn't converge. It wouldn't give me any results. Nope, can't do it. So, a lot of times non-convergence means there's some non-identification somewhere. So anyway, you go back, you kick the computer, you start all over again. But if it did converge, awesome. Right? We get to the part where we get results. First question you got to ask: did the model have good model fit? Did your hypothesized model fit the saturated model? Or fit as well as the saturated model? And that's in this multivariate normal, conditional NBN world. And that right there is also frustrating. I can't tell you the hours spent in grad school, spent in jobs where people have asked me to help them with their data, working on getting model fit, right? Because if you don't have good model fit, then your results aren't going to be accurate, right? So that's this last one. This loop right here is the worst. You're like on the treadmill of models there, right? Or the hamster wheel or whatever else. And then finally, once you get all that done, you can interpret your results, right? And I guess I should have here is p less than 0.05. Not that I agree with it. This is my tongue-in-cheek question and answer. Because if it's yes, then publish or graduate. Sorry. All right, it's a silly system that we're in. Don't get me wrong, the p-values and so forth, but that's what we're after. And if you publish, then the next thing you know, media, grants, tenure. Sorry. There's a big motivation to publish, right? So there's sort of motivation to sort of ignore some of these, like right here, right there, right? Because that's the one that we typically ignore. This one usually gets picked up by reviewers. Nobody really knows this. You're going to have to go that yourself, but you get some wonky results from it. It's this one that's the problem. Anyway, sorry, that's my subjective reality of the map there. All right? So, anyway. So, here's the big model. We're going to try to estimate this thing. Believe it or not. So, here's how the model came about and the data came about. You may find this interesting. I took this paper. I told you this story last week. I took the covariance matrix that they reported and used it to generate multivariate normal data. I did not use this model to generate it. I generated it from the implied covariance matrix of their results. Right? So with that, I could just generate multivariate normal data. In R, the function is, the DM norm that you had to do with the first part of homework? It's RM norm. Take a covariance matrix, take a mean vector, and it will give you numbers that follow a multivariate normal. And that's where these data come from. So I thought that was pretty cool, right? So what we're about to engage in is a model building exercise where this is the model that's been published with an implied covariance matrix, but we're going to find that this model actually doesn't fit, which is plausible. It actually does happen. And I'm not trying to critique the authors. There's a number of reasons where this could happen a little bit, but it's interesting that I took their reported results and I can't come up with a model that's supposed to have reported them to get them back. So it happens. So you'll find this interesting. Here's our model. We had discussed before we had 6 endogenous or dependent variables, 1 exogenous variable. Here you go. Is the model recursive or non-recursive? If you take a look and stare at this, you'll notice all the arrows are moving in the right direction, literally to the right. But those are really what that means is there's no feedback loops present. We can't get to one and then flip back to another from any variable in the model itself. So it is what we call a recursive model. And you're going to hear me call that by accident non-recursive. It just happens. It's just no feedback loops, no circles. What's the, how about the model itself? Let's take a look. How many, if we had 7 variables altogether in the analysis, the number of covariance matrix estimate variables in there here's how you quickly figure out how many unique terms are in the saturated model covariance matrix. It's the number of variables times the number of variables plus 1 over 2. Right? So 7 times 8 is 56 divided by 2 is 28. There's your, if you ever see me start to do math in my head, it's usually that. Like, oh, what's the number of elements in this thing? Believe it or not, you count more than you realize with these models. Counting helps you figure out what the max is. Counting also helps you figure out if your model is, if the computer's doing what you want it to with your model. So I count a lot. And I talk like a Muppet. Maybe I should be the count. Is that your anyone have a favorite Muppet? Is the count up there for any of you? Grover. I like Grover. He's pretty good. Grover? I just like the count. That was pretty awesome. Anyway. Never mind. I'm kind of weird. So how many model parameters? Now you'll note I'm talking only about the covariance matrix here. And these model parameters actually do not involve anything with intercepts or means. Right? So if we only use the covariance matrix, we can kind of get rid of the intercepts and means and just count everything that's not an intercept or a mean itself. Because the intercepts and means show up on the mean vector side, but all these other terms show up on the covariance matrix side. So here we have 12 direct paths. If you go back to our list here, we have 12 arrows. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I got 12. Hey, I counted. 6 residual variances, 1 for each dependent variable. 1 variance of the exogenous variable, which drives me nuts. Our exogenous variable is gender. And we're going to estimate its variance as if it were continuous. But it's okay, I'll be fine. We'll get through this. So there are 19 covariance model parameters right there. And so that means we are actually less than 28. We're good. I said M plus here. The model is what we call over-identified, which just sounds weird, but think of it this way. The saturated model is the goal. That's how you're trying to fit as well as. A model is over-identified when the saturated model has over the parameters that your model has. Right? It's over-identified. Saturated model is like always your comparison. And now you see why I spent weeks trying to build up a saturated model and a covariance matrix, because it's always there. It always shows up. Okay, here are the 6 regressions that we have. These are our 6 endogenous variables, and you'll see they actually show up in other regression statements. So this is why this, again, is a path model. Variables that are dependent variables can predict other dependent variables. Some of you may have learned how to do path analysis by doing a series of regressions separately. Anyone learn that? This method is going away. I never learned that before, but there are people who used to, back in the 1980s and 70s, that's how we did it. But we pretty much do everything simultaneously now because of maximum likelihoods. We just throw it all in the model and we let it run. Whoa, here's analysis. Tell you what, let's take a break for 10 minutes and I'll come talk about this syntax, all right? See you in 10. Thank you.